Hi, Honors Chem kids. Here is another edition of chemistry. So we have finished up chapter 1. By now you should be relatively comfortable in classifying material and matter, and you should be relatively comfortable in understanding chemical versus physical properties and chemical versus physical changes, and have a very basic understanding of the periodic table and where metals are, nonmetals, and metalloids, and how periods are counted. Remember, periods are the horizontal rows, and how groups or families are counted, and remember, they are the columns. Okay, so we're going to get into chapter 2 today. So this is just the next page after the notes that we finished up last time. We're going to get into measuring and calculating. Now, from here, before this class, whenever you've measured or calculated, you've probably only measured and calculated and just reported a number. You haven't really thought too much about what that number means. So today we're going to think a little bit deeper about what exactly that number means and what it's really telling you. So here we go. This is probably a new way of thinking for you guys. Measuring and calculating. Scientific method. You probably have been talking about scientific method in your classes probably since 3rd grade, I would guess. Anyway, my kids, we started doing science fairs at around 3rd grade. So we did scientific method, at least in their schools, at about 3rd grade. So this flow chart right here that we have is pretty much a good flow chart for scientific method. It's a way that we do scientific research. I like to point out that this is an organized way. So we are trying to do a very methodical, organized approach so that we don't miss anything. So let's start here. This is where we start. We make an observation usually, and with that observation, we use our existing knowledge. We use qualitative data. Qualitative data is qualities. Like, for example, my shirt today is kind of a coral color. That's qualitative. Okay. Quantitative data, once again, I'll use my shirt. Like, I could put my shirt on a balance and get a mass for it. That would be quantitative. I like to think of it this way. Quantitative data is numbers. Qualitative data is types or descriptors, okay? And then once we gather all that information from the observation that we've made, we can start to formulate a hypothesis. Why does that phenomenon happen? We might have a couple good solid ideas. The thing about a hypothesis is it has to be testable. It has to be something that we can actually test. So we design an experiment, we get the data, we figure out whether that data concludes and supports the hypothesis or not. If it doesn't, then we revise the hypothesis. If the data and the conclusion is that it supports the hypothesis and we can do it over and over again to the point that it's a good and repeatable experiment, we might make that hypothesis a theory. And then if we experiment, we send it out to other people and they also get the same results, we might actually get that theory to become a really known, broadly accepted theory. And if it becomes so well known and so reproduced over many, many years, over many, many scientists, over many, many tests, it can actually become the scientific law. Okay, so that's pretty much what we talk about with scientific method. Now, one thing I really want to point out is the use of theory. In normal vernacular, when we use the word theory, we're like, oh, it's an educated guess. It's, we really don't have data backing it up all that much or whatever. We might have some. But notice in scientific language, when we use the word theory, not only do we have countless experiments in this realm, but we've also broadened it out to lots of other people to do the same experiment and make sure that it's reproducible for them. And over many, many years, that's when we finally get to the theory mark. So when we talk about a theory in science, we are talking about years and studies, like many, many studies to get to that point. It is not something that we just are thinking about. It's something that we have a significant amount of data to support. Okay, so let's go through a scientific method and we'll ask some questions. So here's my example. Why we're getting to fall here in a month or so, why do leaves change color in the fall? So, hypothesis. The number of hours of daylight change from summer to fall, right? We have summer daylight to fall, so our number of hours of daylight goes down in the fall, right? Perhaps fewer hours of light triggers that change color. Okay, so how would you design that experiment to test for fewer hours of light? Take a minute, pause, write down your notes, write down your thoughts of how you would test that. Okay, so for me, I would need to have a controlled greenhouse, several of them. So I would need to have a greenhouse, probably several of them, where I can control the amount of light. And I would probably do that with grow lights. Okay, there's special LED lights that have broad spectrum on them so that the plants can get all the wavelengths of light that they need. Specifically the green and red and blue lights that the chlorophyll pick up. I would also need to have multiple places that I can separate from each other to change the amount of light. Okay, so one room, I would probably do 2 hours of light. Another room, I'd probably do 3 hours of light, and so on, probably for multiple rooms. And I would want to have many different amounts of light that are being tested. I would also have to put in what we call controls. Controls are things that we keep the same so that we know that the change that we are seeing is only due to that one thing that we are really changing. So the one thing that we are changing here is the amount of light. So we want everything else to be the same. So we're going to want the soil to be the same. We're going to want the temperature to be the same for those plants. We are going to want the type of plant to be the same. We're going to want to make sure that the plants are given the same amount of water. We're going to want to make sure that the humidity is the same in that room, and on and on and on. We want to keep everything else the same. Okay, so what do you think our conclusion would be? Would we find that changing the amount of light that these plants are exposed to would trigger that color change? Actually, we would find that it's actually the amount of dark that the plants are exposed to. So we would actually have to revise our hypothesis. Okay, so we would probably also want to cycle this with dark hours here. So a lot of scientists and botanists have done this, and they've actually concluded it's not the light, not the amount of light that triggers this. It's the length of night or dark that triggers that. So they usually put the amount of light backed up with very minimal dark so that they could actually see how much was going on with the light versus the dark. So the revised hypothesis that botanists actually had to go to was not focusing on the amount of light, but the length of the night or the amount of dark that the plants were exposed to. And that's where they actually got the correspondence. Okay? All right, now to measurements. Measurements in science. You may think that the terms accuracy and precision mean the same thing. And in normal English vernacular, we do use them kind of interchangeably. But in science and in tech, they do not mean the same thing. Okay, so accuracy. Accuracy is how close you are to the accepted value. How close your measurement is to the accepted value. So, for example, say I had one of those really fancy laser measuring tapes, and I was measuring the size of a room to maybe get new carpet or new flooring put in, and I knew that my room was 14 feet long. If I actually took a normal measuring tape out and I got a measurement of 14 feet and 11 and a half inches, I would be off by half an inch. That would be my error right there. So how close I am to the actual value of 14 feet, if I know that a room is actually 14 feet long, how close am I to that actual value? That is what accuracy is. Okay? Precision is if I can do the same thing the same way over and over again. Can I do it exactly the same? Can I get that same measurement the same way over and over again? So it's basically how close a group of measurements are let's see, how close a group of measurements of something is to each other. Okay, so if I measure a pencil, for example, and I measure it the first time and I get a measurement of 7 inches, and the next time I get a measurement of 7.12 inches, and the next time I get a measurement of 6.9 inches and 7.3 inches, that's not really accurate, or it's not really precise because I'm getting different measurements all the time. I would be really excited if I could get 7.12 over and over and over again each time I measured it. That is precision. How close all of the measurements of that same object are to each other. So let's look at these representations here. So accuracy, once again, we want to hit that bullseye, and that arrow hit the bullseye, so it is accurate. Okay? Right here, I'm doing the same thing over and over again, and I'm shooting right on top of each other. So I am precise. I am able to repeat that over and over again in the same way, but I'm not hitting where I want to be. So that is precise, but not accurate. Here, I am both accurate and precise. So I can repeat over and over again, and I can hit the right spot. So I'm precise and accurate. Here, I'm not accurate or precise. I'm not hitting the same spot, and I'm not hitting the right spot. So I'm neither precise nor accurate here. Okay? So when we make measurements in the laboratory, what determines how accurate we can do? What really determines our accuracy is our measuring tool. Okay? Measuring tools can be accurate or not. Usually the amount of money that we spent on that measuring tool is what determines the accuracy. For example, if I really wanted to measure the length of something really, really well, would I use a ruler or would I use a caliper? I would use a caliper. Calipers, I don't know if you guys know what a caliper is. You might want to look it up. Calipers are pretty expensive, but I can get measurements down to the 0.001 of a centimeter on good calipers. They also are expensive. I can get a ruler for like, what, $1 at the grocery store or at Target. Caliper is going to set me back a little bit more. What determines precision? How well I can do the same thing over and over again. Did you notice I said how well I can do the same thing over and over again? What determines precision is you, your lab technique. Okay, your lab technique is what is the determinant of your precision. Okay, so let's take a look at some of this this data here. So we got 3 students. We've got student A, student B, and student C. And let's take a look at their data. They were measuring the same thing. So we've got trial 1, 2, and 3 for each of them. And we have their averages here. Okay. The accepted value for this is 1.59 grams per centimeter cubed. By the way, centimeter cubed is equal to milliliter. So that gives you kind of an idea of how that rolls out. Let's redo milliliter. Okay. So we've got trial 1, student A, we've got 1.54, and here we've got 1.60, and here we've got 1.70. So what I really like to do to find precision is look at the range. The range is the top number minus the bottom number or the lowest number. I shouldn't say top. I should say lowest and highest. So our highest number here is 1.6, and our lowest number here is 1.54. So here our range, and I'm going to put it here, is 0.06. Okay? Range is a good indication of precision. Okay? Here, let's look at student B. We got 1.40, 1.68, 1.45. So our top number is 1.68. Our lowest or our bottom number is 1.40. So our range here is 0.28 grams per centimeter. I should put grams per centimeter cubed here. Okay, always have your units here. And then here I've got 1.70, 1.69, and 1.71. So my highest number is 1.71. My lowest number is 1.69. So my range here is 0.02 grams per centimeter cubed. Okay, so let's look at all of these ranges here. So this has a huge range, 0.28. So we know that we do not have precision here. That is not precise at all. This set, though, is pretty precise. That's really good data right here. Okay, but if we look at this for accuracy, though, we want it to also measure really close to this. This, by far, is our most accurate measurement. So what we can say here, though, this is accurate. The precision is pretty average here. This is not very accurate, nor is it precise. This data isn't very good. This is very precise. So this person has really excellent lab technique. But what we can say about this right here is their measurements weren't very accurate. So that means that their balance that they were using, or one of their measuring tools that they were using, was not calibrated, meaning that it wasn't aligned with what it was actually measuring. So I would go back and recalibrate one of the tools, whether it was the balance or the volume that they were using. Okay? So, scientific notation. How many of you guys have done this in your classes before? We use scientific notation in chemistry a lot, because sometimes we are using really big numbers and sometimes we are using really small numbers. So when we do that, we want to use scientific notation so that we're not caught up counting all those zeros, because I don't know about you, but when I count those zeros, I sometimes lose my place. So if this is your other plug, if you don't have a scientific calculator yet, let's see, this, or maybe even this version, get one, because we're going to start using them like this week. You're going to want them. Okay. I'm going to use this for demo purposes. Okay. So I want to write these following numbers in scientific notation. So scientific notation, the rule is we want the number to be somewhere between 1 and 10. And then we will do the power of 10 by a times 10 to some number up here. So that could be any number. So let's look at this. So I'm going to want to put my decimal point right there. So this is going to be 2.45. And then how do I decide the power of 10? Well, I have to count how many spaces that I had to move that decimal place. So I had to move it 1, 2, 3, 4, 5, 6, 7, 8 spaces. Now I had to move that from here to here. So the rule here is if I'm moving it to the left, it's going to be a positive exponent. So this is positive 8. So this is going to be 2.45 times 10 to the 8th. Now notice here, I'm going to want to put my decimal place here. So this is going to be 3.4. Now let's figure out, I'm moving my decimal place this way. So I know that this is going to be times 10 to the negative something, because anytime I need to move my decimal place to the right, it's going to be negative. Let's count how many spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is times 10 to the negative 11. Okay, notice I tried to group these in threes to make it a little bit easier for you to count. Okay, so we could just count 3, 6, 9, 10, 11. That will make it easier. Take a minute, do these next two. Okay, you ready? So this, I'm going to put my decimal place here. So 6.02, let's see, 2, 5, 8, 11, right? 14, 17. This is going to be times 10 to the 17 here. Okay, and this really, if it's just one decimal place, it's not really worth moving. Same with this. This would really just be one decimal place. So I'm okay with you leaving it the way it is, but this, by all technical means, would be 1.0004. Did I put an extra 0 in there? 1, 2, 3. Nope. 1, 2, 3, 4, 5 times 10 to the 1, because I just moved it to one spot. And I put the decimal place here, 1.4 times 10 to the negative 1. How did you guys do on that? Okay. All right. Next thing, significant figs. We call these sig figs. So significant figures. It is a concept that we use a ton in chemistry, and we use a ton in physics as well, and engineering if you ever go into the engineering field. So you're going to want to learn this if you want to go into any of those fields. So I've got this cutout of this paperclip here. And if I want to record this measurement to the correct number of significant figures, we can always estimate one, just one digit. So when we're looking at this, I've got centimeters, and we're going to use the centimeter side because, let's be honest, this is science. So we're going to use the metric system. I know for sure I've got 5 centimeters, but I don't have 6. So I can start this out with 5, and that will be a point. Let's see. These are now millimeters. So I've got 1, 2, 3, 4, 5, 6, 7, 8 millimeters. I know for sure I've got 8, but I don't quite make it to 9. So I have 5.8, and then this digit, I don't have any more lines. So I need to look in between these two right here and say, okay, am I a little bit more than halfway, less than halfway? I need to eyeball that into tenths if I can. So I think looking at this, I'm a little bit more than halfway. In fact, I think I'm about 5.87. Would you be equally correct in writing down 5.86 or 5.88? Yes. Notice all of these, that last digit is just our best guess. We really don't know it for sure. So significantly, that's all we can do. If I wrote out any more numbers after this, it would just be an absolute lie because I have no information to give me any information beyond that number. That's why we call it significant, because these are the ones that we actually have some data to tell us about. Okay? So how many estimated digits can I include in a measurement? Just one. That last digit is always going to be an estimation. Okay, I can only do one estimated digit in a measurement. Okay, so for example here, I know for sure I've got 5 centimeters. I know that. I know that I have 0.2, but in between 0.2 and 0.3, I don't know exactly where it falls. I know it's closer to 0.2 than it is to 0.3, so I'm going to estimate that as 0.03. So I would write this as 5.23, but remember that 3 is estimated. Okay, so those are the only significant numbers I have on that measurement. Anything else would be absolutely a guess. Okay, let's go on. So let's look at this. Here I've got the same line on 2 different rulers. Notice this ruler has tenths here. This ruler does not. So I really, for this ruler, I know for sure I've got 2. And I know it's somewhere between 2 and 3. So the best estimate I can give is it's about halfway. So this is my estimated digit. But notice if I have these tenth markings in here, I can give another digit. So here I know it's 2 for sure. I know it's 1, 2, 3, 4, 5. I know that one for sure. I know it's somewhere in between 5 and 6. And to me, it looks like it's right smack in the middle. So I'm going to estimate that as 2.55. This is my estimated digit. So notice your precision, not your precision, your accuracy is totally dependent on your measuring tool. The more accurate your tool is, the more ways it has to subdivide things, the more accurate you can be. If your measuring tool is not very good, you're not going to be able to get a very accurate or informative number for your data. Okay, so what is the volume of this liquid in the graduated cylinder? Now remember, hopefully in biology, you guys were taught that water will actually curve in glass. Do you see that? We call that curve a meniscus, okay? Because it's kind of like the meniscus on the underside of your patellar kneecap. That's why that's also called a meniscus. We've got this curve here. So we always read from the bottom of that meniscus, so right here. Because different cylinders the water will climb up to different degrees on the side. So we're always going to read from the bottom. So we have the same measurement every time. So I know for sure I've got 41, 2, 3, 4. So for sure, I know I've got 44 milliliters. I know I'm somewhere between 44 and 45 right in here. Now, to me, it looks to me like I'm a little bit closer to that 45. And I'm going to measure that as a 0.8. Would I be equally accurate in saying 44.7? For sure, because once again, that last digit is an estimation. So that last digit is always your best eyeball guess. Okay? All right, and here we go to sig figs. Significant figure rules. This is a way to do math that you have not really been doing before. So the way you're going to have to look at this is we're going to look at, that's not what I wanted to do. You're going to have to look at things a little bit differently, okay? So we have a way that we look at whether a number within a number is significant or not. So let's look at the rules here. Rule number 1, non-zero numbers are always significant. So 72.3 has 3 significant digits. All non-zero numbers are always significant. Rule number 2, all final zeros to the right of a decimal are significant. I wouldn't just say to the right of a decimal, I would say to the right of the non-zero numbers. With a decimal. Okay, that's how I would phrase this. So all final zeros to the right of the non-zero numbers with a decimal are significant. So here, I've got a 0 to the right of a non-zero number, and the number has a decimal in it. So that 0 is significant. So the 6, the 2, and the 0 are all significant. Rule number 3, any 0 in between non-zero numbers or significant figures is significant. So I have 60.5. That 0 is holding a place between non-zero numbers, so that is significant. So all 3 of those numbers is significant. Placeholder numbers are not significant. So it's really easier to rewrite these numbers in scientific notation. So if I have placeholder numbers, once again, we have to look and see if there is a decimal point in here. So here, notice this 0 is to the left of the non-zero numbers. Remember, to the right of the non-zero numbers up here, if it's to the left of the non-zero numbers, even if it's behind a decimal point, it is not significant. So I could write this as 2.53 times 10 to the negative 2. And here, this number, 4,320, has no decimal point in it. So I know that if a number has no decimal point in it, the zeros in that number, whether they're before or after, are going to be insignificant. So I could write this as 4.32 times 10 to the 3. I don't even need to use that 0, okay? So those are each going to have 3. Rule number 5, counting numbers and defined constants have an infinite number of significant figures. So we are going to think, I have 6 molecules. That has, I can count them, 1, 2, 3, 4, 5, 6. I have 6 molecules. So that has an infinite number of significant figures. And any definition like this, 60 seconds equals a minute, that is a definition that is also going to have an infinite significant figure. Okay, so I am going to leave this at this. We are going to review this a little bit next week, and we will talk about sig figs some more times. We'll see you. Bye.